This is an interesting integral that provides good practice on how to do some basic integral operations in the vector context. So remember that if you want to take the integral of a vector valued function, it's as simple as just integrating each component separately. So let's look at how to do that. First of all, for the x, it's going to be the integral from 0 to 1 of 4 over 1 plus t squared dt. This might make you reach for some kind of u substitution or something like that, but u substitution only works when there's a du to cancel out with the u. So if you choose u to be 1 plus t squared, your du is going to involve a t, and you're kind of out of luck. But this is one of those things where you just have to recognize that this fits together with an existing function that you already know. And these are hard to remember, but remember this: the derivative of inverse tangent of x is 1 over 1 plus x squared. Now, I don't mean that you need to memorize each individual one of these formulas, but if you want to be able to do these problems successfully, you need to have maybe some kind of reference sheet or something like that that will let you comb through and say, what format does this match? And this matches this format. It's so close. It's just off by a factor of 4. So really, this is going to be 4 inverse tangent of t evaluated at 0 and 1. So this will be 4 inverse tangent of 1 minus 4 inverse tangent of 0. Well, what are those? Inverse tangent of 1, what has a tangent of 1? It's pi over 4. So this is 4 times pi over 4 minus 4 times, and what has a tangent of 0? Remember that this is within the bounds negative pi over 2 to pi over 2. That's the range of inverse tangent. Within that bound, the only thing that has a tangent of 0 is 0 itself. So this is 4 times 0. 4 times pi over 4 is simply pi, and 4 times 0 is 0. So this is pi. That's the x component. This is half of it. We now need to go and find the y component. Integral from 0 to 1 of 2t over 1 plus t squared. Small differences make big differences in calculus, because although the previous problem was an inverse tangent, this is not. This actually is u substitution, because here on the bottom you've got the t squared, and on the top you've got a t factor. That means that the u on the bottom, the 1 plus t squared, is going to cancel with the top once you take the du. Now there are a couple ways to do this. Hopefully you'll recognize that the way that we're doing it here is equivalent to what you're doing in your class, even if it might not look exactly the same. If we take u to be 1 plus t squared, and then that makes du equal to 2t dt. Sometimes I like to solve for dt and plug it back in, but sometimes it's just so clear that it's right there. So 2t dt is exactly what du is, all right? Where I differ from how some classes do this is that I tend to leave the bounds of integration in terms of the original variable and then convert back at the end. So this is integral from t equals 0 to t equals 1, now of 1 over u du. 1 over u as in 1 over 1 plus t squared, and du is the 2t dt part. Well, this is easy now. This is going to be ln of u over the bounds t equals 0 to t equals 1. And this is where I convert back to the original variable to make it make sense. So this is ln of not u anymore, but 1 plus t squared from 0 to 1. ln of 1 plus 1 squared is ln of 2. ln of 1 plus 0 squared is, oops, I should be doing subtraction, minus ln of 1 plus 0 squared is 1, ln of 1. And everybody who knows anything knows that ln of 1 is 0. It is egg, nada, zilch. So this is ln of 2. So this integral is equal to an x component of, nope, vector brackets, please. Well, I'll do I and j. It is pi I plus ln2 j. Because the function is a vector, a simple integral of it, not a line integral or anything fancy like that we'll do later, but just a normal integral is itself a vector. And we have the answer.